What if charging your electric vehicle to 80% took less time than ordering a coffee? When Donut Lab announced that its solid-state donut battery could charge from 0 to 80% in just 4.5 minutes at an 11C rate, it sent shockwaves through the battery and EV industries. In a world where even the fastest lithium-ion vehicles typically require 20 to 30 minutes to reach 80% under optimal fast charging conditions. But is this a genuine technological breakthrough? Or is it a bold marketing narrative built on carefully selected test conditions? Let's deep dive into this episode today and become our first subscribers for the channel. Thank you, fellas. To understand the magnitude of this claim, we need to first decode what 11C actually means. A C rate defines how fast a battery is charged or discharged relative to its capacity. A 1C rate means charging the full capacity in 1 hour. An 11C rate theoretically implies a full charge in roughly 1/11 of an hour, or about 5.5 minutes. Reaching 80% in 4.5 minutes is consistent with that definition. But here's the key question. Can a battery absorb energy at that rate without catastrophic heat buildup, structural damage, or rapid degradation? At the heart of Donut Lab's technology is an all-solid-state architecture. Unlike conventional lithium-ion batteries that rely on flammable liquid electrolytes, solid-state cells use a solid electrolyte to conduct lithium ions between the anode and cathode. This eliminates leakage risks and significantly reduces the likelihood of thermal runaway. Without liquid electrolytes, the formation of lithium dendrites, needle-like metallic structures that can cause short circuits, is theoretically suppressed. But does eliminating liquid truly eliminate risk? Not entirely. Even solid electrolytes can crack under mechanical stress, creating pathways for dendrite growth if not engineered properly. Donut Lab also claims an energy density of 400 watt-hour per kilogram. To put that into context, most high-performance lithium-ion packs in premium EVs operate between 250 and 300 watt-hour per kilogram at the cell level. Crossing the 400 watt-hour per kilogram threshold would nearly double the gravimetric energy density compared to mainstream EV packs just 5 years ago. What does that mean in practical terms? A 100 kilowatt-hour battery pack could potentially weigh 250 kilograms instead of 400 kilograms, drastically improving vehicle efficiency and range. But achieving 400 watt-hour per kilogram in a laboratory coin cell is very different from achieving it in a large automotive-grade pouch or cylindrical format. The question engineers always ask is, what is the pack-level energy density after accounting for cooling, casing, and safety systems? Then there is the astonishing claim of 100,000 charge cycles. Conventional lithium-ion batteries in EVs typically last 1000 to 3000 full cycles before dropping to 80% capacity. Even lithium iron phosphate chemistries, known for longevity, rarely exceed 5000 cycles under real-world conditions. So what does 100,000 cycles actually mean if true at full depth of discharge? It would represent decades of continuous use, far beyond any current automotive requirement. But here is the engineer's skepticism: at what depth of discharge? At what temperature? And at what C rate were those cycles measured? A battery can achieve extraordinary cycle life under shallow cycling and moderate currents. The challenge is maintaining that longevity at 11C charging. Independent validation from VTT reportedly confirmed the 11C charging performance, achieving 80% in 4.5 minutes and full charge in about 7 minutes. That sounds definitive. Yet the real story hides in the thermal data. During ultra-fast charging tests, cell temperature reportedly rose from approximately 26 degrees Celsius to around 63 degrees Celsius, and in scenarios with insufficient cooling, could approach 90 degrees Celsius, a common safety cutoff threshold. So we must ask, can this technology truly scale without aggressive thermal management? At 11C, resistive heating scales with the square of the current. Even small internal resistances generate enormous heat at such high currents. If cooling fails, degradation accelerates rapidly. And what about infrastructure? To charge a 100 kilowatt-hour EV pack to 80% in 4.5 minutes requires delivering roughly 80 kilowatt-hour in 270 seconds. That translates to a power level of nearly 1.1 megawatts. Today's most advanced public DC fast chargers operate at 350 kilowatts. Deploying megawatt-level chargers would demand significant upgrades to local grid transformers, cabling, and buffering systems. Are power grids ready to handle multiple vehicles simultaneously pulling over 1 megawatt each in dense urban environments? The answer is likely no, at least not yet. Still, imagine the impact if these barriers were overcome. Would range anxiety disappear overnight? If charging truly felt like refueling a gasoline vehicle, EV adoption could accelerate dramatically. A driver could stop, take a short break, and leave with nearly a full battery. Combined with 400 watt-hour per kilogram energy density, vehicles could either extend their range well beyond 700 or 800 kilometers per charge, or maintain current range while shedding hundreds of kilograms. Reduced mass improves acceleration, braking, and overall energy efficiency. That's not incremental improvement, that's a structural shift in vehicle design philosophy. Now consider electric aviation. Could ultra-fast solid-state batteries unlock practical short-haul electric flights? In aviation, weight is everything. Every kilogram saved in battery mass translates directly into additional payload or range. If a regional electric aircraft required rapid turnaround times comparable to jet refueling, 4.5-minute charging could dramatically increase utilization rates. Airlines depend on aircraft flying multiple cycles per day. Slow charging would ground electric planes for hours. Fast charging could make them commercially viable. Furthermore, solid-state chemistry's resistance to fire is critical for civil aviation certification. No aviation authority would approve a battery prone to thermal runaway at 30,000 feet, but skepticism remains justified. Solid-state batteries have been 5 years away for over a decade. Manufacturing challenges persist. Solid electrolytes must be defect-free and uniformly dense across large areas. Even microscopic cracks can compromise performance. Scaling from laboratory prototypes to gigafactory-level production introduces yield problems, cost overruns, and reliability variability. Can Donut Lab produce thousands, then millions of identical high-performance cells without performance drop-offs? History suggests that scale reveals weaknesses that laboratory testing hides. Cost is another unresolved variable. Solid-state materials and processing methods remain more expensive than mature lithium-ion supply chains optimized over 3 decades. If 400 watt-hour per kilogram cells cost twice as much per kilowatt-hour as existing lithium-ion packs, automakers may hesitate despite performance gains. Consumers ultimately buy vehicles based on total cost of ownership, not charging headlines. So, what happens after 1000 real-world fast charge cycles? Does capacity retention remain above 80%? Does internal resistance increase significantly? Leave a comment below if you already has the answer, and also discuss future tech. Thank you, fellas. Before you leave, please help us reach our first channel subscribers, and don't forget to click that bell icon to quickly receive notifications about upcoming exciting content. Thank you, fellas.